All right, guys, so let's go ahead and go over this because y'all should have no problem answering this question. Okay, so I'm going to ask you to, again, direct your attention up here. It says, when a cannon fires a cannonball, why is the speed of the cannon's recoil less than the speed of the cannonball? And this is what we were talking about in the notes 2 days ago, but we talked about it last semester as well. Maybe you saw this in your RA yesterday, which, by the way, is due next Wednesday. Not with the cannon and the cannonball specifically, but with the motion of two objects moving away from each other. So let's talk about why that is, because obviously they do go off in opposite directions, and the cannonball is definitely faster than the cannon. But we know that the change in momentum of the cannon and the cannonball are equal and opposite. Okay, we talked about this in our notes 2 days ago when we talked about the law of conservation of momentum. And so we know that whatever momentum that the cannonball has afterward, the cannon has equal and opposite momentum. So we could say this: the mass times change in velocity of the cannonball equals the mass times change in velocity of the cannon. Again, since they're opposite, it'll be m delta v equals negative m delta v, since they're in opposite directions. The mass of the cannon, though, is much larger than the mass of the cannonball. So whenever you look at that equality statement that we just wrote up there, because their masses are so different, so will be their changes in velocity. Okay, so the change in velocity for each is, again, inversely proportional to its mass. And so you have that cannon that has a large mass will have a small change in velocity, whereas the cannonball, which has a smaller mass, will have a large change in velocity due to the same force acting on both of them. Okay, again, coming back to stuff from last semester as well, since there's an equal impulse, same force pair, same time, okay, then you're going to have same change in momentum, which means the mass times change in velocity will be equal for each, at least in magnitude. Obviously, the direction is opposite. Okay, so you get this. So again, make sure that you have answered your warm-up question, but the reason that that cannon has a slower recoil velocity is because it has greater mass than the cannonball while having equal momentum afterward, an equal change in momentum as well, since both of them started at rest. Okay, so again, we talked about conservation of momentum in our notes 2 days ago, and we said that in a collision, the momentum change of object 1 is equal to and opposite of the momentum change of object 2, just like our cannon and our cannonball, but it doesn't have to be a cannon and a cannonball. It can be two billiard balls, it can be two physics carts like in the RA, it can be any two objects that collide. Whenever you have a collision, you're going to have equal and opposite change in momentum for those objects so that the total amount remains the same. That's the whole idea. If one of them loses, let's say 50 kilogram meter per second of its momentum, the other one will gain that much so that the total change of your system is 0. Okay, and that means that you have conserved that momentum. And so the example here has a cue ball and a striped ball, and it's the same idea. If the cue ball initially has 100 kilogram meters per second momentum and it stops, which it does in this animation, then its change is negative 100. The striped ball, on the other hand, that starts at rest, will have positive 100 as its change, so that the total change of the system ends up being 0. They cancel each other out. Negative 100, positive 100. No change for the system overall in terms of its momentum. Okay, so again, that's conservation of momentum. You have to have the same amount before the collision as you have after the collision. And if you haven't done the calculations yet in your RA, you're about to see that with the numbers that you collected yesterday. All right, so we do have an equation for it, and we've kind of been doing this in pieces. We haven't done it all at once, but y'all did this, or you will be doing it in the RA, and we've been talking about it with the cannon, cannonball, whatever examples we have done. But again, conservation of momentum states that the total initial momentum of your system equals the total final momentum of your system. And so you can't have a change. The total change is 0. Whenever we talk about initial momentum, we have mass times velocity, that's momentum. So because our collisions are going to involve two objects, now technically they could have more, but in this class we're going to stick with 2. You're going to have an equation that looks like this. m1 v1, that's the mass of object 1 times the velocity of object 1 initially, plus m2v2 initially, so that's the initial momenta of each object added together, equals the final momentum of each object added together. That's m1v1 final plus m2v2 final. Okay, and so that right there is going to show that your total initial momentum is going to equal your total final momentum. That's the law of conservation of momentum. You can see it with this animation down here. I'm not going to use these numbers, but if you were to try this out, in the before and after, you can see that this statement holds true and that momentum is conserved in that collision as well. Okay, so again, this is our equation for conservation of momentum. m1v1 initial plus m2v2 initial equals m1v1 final plus m2v2 final, where 1 and 2 represent the objects that are colliding. It does not matter which object you call 1 and which object you call 2. Okay, since the order in which you add them doesn't matter. Just make sure that you keep them straight and you know which one is moving at which speed, because you do need to make sure that you group those correctly. All right, so again, going back to the warm-up question, what can you tell me about the initial momentum of the cannon and cannonball before they're fired? What is the momentum before it's fired? 0, because they're both at rest. The cannon's just sitting there, the cannonball's just sitting there in the chamber, nothing has happened, there's no explosion yet, and so initially, because both are at rest, the momentum of each is 0. And this is going to be true for the recoil collisions that we deal with in this course. Now, I know in the simulation there was a way for you to give it a velocity, and I'm sure you probably did. I think I asked you to do it with one of them. But in our calculations, they're always starting at rest. Okay, if they are moving, they're moving together, but we're going to say that they start at rest. Okay, and so if the initial momentum of the system is 0, what must be true about the final momentum of that system?
0.
Has to be 0, which means that if you look at them separately, because they need to total 0, they have to have equal and opposite momentum. Okay, and so that's what it says. The momentum of the cannon must be equal and opposite to the momentum of the cannonball because they must total 0. This is going to be the case for all of our recoil calculations. Okay, because they start out at rest together, their final momentum also has to be 0, which means that those two objects have to have equal and opposite momentum. Now, that doesn't mean equal and opposite velocity unless they happen to have the same mass. Okay, but otherwise, they're going to have different velocities, but their momentum needs to be equal and opposite so that the total momentum of the system is 0. All right, so again, this is in every recoil or explosion collision. We start out with an initial momentum of 0. Now, I could still write m1v1 initial plus m2v2 initial, and when I solve that whole side, it's going to be 0. And so I have that initial 0 momentum is going to be equal to, this is to shorten it, if it's recoil, you could do this, is equal to m1v1 final plus m2v2 final. And you could rearrange that even further to say that this, m1v1 final equals negative m2v2 final, which is what we just said. The momentum of these objects have to be equal and opposite. Okay, there it is mathematically as well. They have to have equal and opposite momentum at the end of that explosion. Okay, the cannonball is shot forward, the cannon moves backward or whatever, depending on what direction you're calling forward. But they move in opposite directions as the point, and so the two have equal and opposite momentum. This will always be the case. And again, it doesn't have to be a cannon and a cannonball. The two carts in the simulation the other day had a spring between them. Same thing. That spring applies a force to both, and it moves them with equal and opposite momentum. All right, so let's try a calculation with some numbers. Again, you might want to jot this down. It says a 153 kilogram cannon fires an 8 kilogram cannonball at 74 meters per second. Find the cannon's recoil velocity. Whenever I do conservation of momentum, a collision, I find it helpful to draw a picture, a before and an after. And so that's what you see up here is my before, my initial state and my final state. Initially, they're both at rest before it gets fired. And the question's not going to say that, by the way. The question's not going to say the cannon and the cannonball are initially at rest. It's going to be implied that before it gets fired that it's not moving, okay, unless it says otherwise. And so we're going to have our initial velocity of 0 for both of our objects. They're going to start out together. And then after it's fired, I know they're going to do this. I know they're going to move in opposite directions. I know that my 8 kilogram cannonball is going to move 74 meters per second. It's in the question. And I have to figure out how fast my 153 kilogram cannon is going to move after that collision. Okay, so if we want to look at that, we're going to start by labeling all of our givens and our unknowns. And we're going to have our mass of object 1, and this is where it gets tricky, guys, and you really do need to make sure that you keep it straight between object 1 and object 2. I'm calling object 1 my cannon. It doesn't matter, it's arbitrary, as long as you know this one's 1 and this one's 2, so you can keep your data straight. My initial velocity of object 1 is 0. Object 2 is my cannonball. It has a mass of 8 kilograms. Its initial velocity is also 0. Okay, and looking at the after, again, we're separating this into before and after. Afterward, I still have my cannon 153 kilograms, and we're looking for how fast it's moving. My cannonball, again, M2. Notice that I made sure M1 stayed the same object on both sides. Make sure you do that. Okay, and M2 as well. 8 kilograms is now moving 74 meters per second. Okay, so we have all of our given information. And we're going to substitute it into that equation that I just gave you a moment ago. The total initial momentum of the system, which is the initial momentum of object 1 plus the initial momentum of object 2, that's the total, equals the total final momentum of the system, that's the final momentum of object 1 plus the final momentum of object 2. And again, I know that momentum is m times v. So you get this. This is the same equation that I had on the screen a second ago. And I have highlighted what we're looking for. So we're looking for this final velocity of object 1 because I called the cannon object 1. Okay, so from here, we're going to substitute in. Okay, all those values are going to go into that same equation that we just learned. And again, I already told you that we're going to have a shortcut here. What's my initial momentum? 0, yeah. Edward said it. But yeah, look, with a recoil, my initial momentum is 0. Okay, I could have just plugged in the 0, but you're still going to get 0. 153 times 0 plus 8 times 0, 0. Okay, so your initial momentum of your system is 0. Okay, your final momentum, you're going to take your mass times your velocity 1, mass times velocity 2, you get this. Okay, now, algebraically, here's where some of you are doing weird stuff. Please do not add those numbers together. 153 times V1F cannot be added with 592. They are not like terms. That is not how you algebra. Don't do that. Okay, so if you're trying to solve for your final velocity of object 1, you're going to subtract that 592 from both sides. But again, sorry, I forgot that was on there. Your total initial momentum was 0. We already determined that, so we know the total final has to be 0. Okay, but you're going to get this. Okay, and then you're going to divide both sides by 153 because, again, you're trying to isolate this variable so you can solve. So that is what goes in your calculator. Okay, negative 592 divided by 153 is going to give me a final velocity of negative 3.87 meters per second. And again, make sure it makes sense. Is it going the right direction? We just said they have to move in opposite directions. This is 74, this is negative, yes. They need to be in opposite directions. Make sure it makes sense. Should this be moving slower?
No. Yes.
Yeah, well, slower than this for sure. Not necessarily slower than this. This is right. Okay, but this should be moving slower than this. It is. That's a lot slower. It's also a lot more massive. Okay, so make sure your answer makes sense. Okay, are there any questions about this one? This is what all of your recoils are going to look like. Yes, sir.
Did you just multiply the mass and the velocity divided by
Yep.
the mass and that's so you get just put the negative.
Just plug it in. All right, so again, total momentum in the system before a collision must equal the total momentum after the collision. Look at our numbers now that we have them all. Okay, my initial momentum is 0. Let's make sure that our final momentum is 0. It needs to be. Okay, so our final momentum, if we were to plug that back in, 153 times negative 3.87 plus 8 times 74, it gives us 0. It should, but you can double check it that way too. Okay, make sure that you have the same amount before and after your collision. And that's what it's going to look like for every single recoil, every single explosion. All right, here's another practice problem. This one's not recoils, but it's a different practice problem. It says, 2 grocery carts collide, one full with a mass of 35 kilograms moving east at 2 meters per second, and an empty one with a mass of 10 kilograms moving west at 3 meters per second. Notice I didn't put a negative and a positive, I put east and west. Please make sure that you pay attention to that whenever you are labeling things. Okay, after the collision, the full cart is moving east at 0.75 meters per second. What is the velocity of the empty cart? So again, we're going to draw a picture. I told you that that's always a helpful tool. So we have our 35 kilogram cart moving east. I'm going to say east is to the right of my screen, so I have my 2 meters per second labeled moving to the right. My 10 kilogram cart is moving west at 3 meters per second, so I've drawn it going the opposite direction. When I label those numbers in a minute, I'm going to call that the negative direction. So again, make sure that you do that. Make sure you have your signs right. But that's beforehand. And then we have the after the collision happens. Afterward, my 35 kilogram cart is now moving 0.75 meters per second in the same direction it was already moving. It's still going east. That's what it says. Okay, and the question is, what is this one doing? Not just how fast, but we don't even know which way yet. Okay, that's why I just put question marks. I'm assuming it's moving. Okay, I don't know for sure. We have to calculate it. So the question is, how fast is it going and which way? What is its velocity? So there's my picture that summarizes everything that was in the question. That's why it's helpful to draw those out. Okay, from here, you're going to label those given. So again, I'm going to call the red one 1 and the blue one 2. Okay, so M1 is going to be 35 kilograms with an initial velocity of 2 meters per second. M2 is going to be 10 kilograms with an initial velocity, and look at that, there's my negative sign. Remember, make sure that you pay attention to that. If they're going opposite directions, you need to have that negative sign. Negative 3 meters per second. Okay, and then afterward, still the same mass, those aren't going to change, 35. And the velocity afterward for that one is 0.75, 10 kilograms. I need to find its velocity. So there's my unknown. And it's the same equation, no matter what type of collision we're doing. Same formula. We still need to use conservation of momentum. I know the total initial momentum of my system needs to equal the total final momentum of my system, but I don't really want it in terms of P. I want it in terms of M and V because that's what I have. So I have M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final, and we're looking for that V2 final. Okay, I've highlighted it. That's what you're going to solve for. So if we substitute into that equation, we get this. And again, copy it down and make sure you copy the signs, otherwise you're going to get the wrong answer. 35 times 2 plus 10 times negative 3 equals 35 times 0.75 plus 10 times V2F. I'm sure you could probably solve it from here. This is just algebra from this point. Okay, so when I solve that, that is an initial momentum for object 1 is 70. For object 2, it's negative 30. You can see each piece as well whenever you do the whole process. Okay, my final momentum of object 1 is 26.25, and again, we're trying to figure out what object 2 is doing. So again, here is my total initial momentum, 40. I can see it right there. It's the whole left-hand side of the equation. Good. Okay, so we have 40 equals 26.25 plus 10 times V2F. We're going to subtract that 26.25 from both sides, and we're going to get 13.75 equals 10 times VF. And if we want to solve for that V2F, we're going to divide both sides by 10. And our final velocity of our 10 kilogram object is 1.375 meters per second. Notice it's a positive number, which means I not only know how fast, but I also know it's moving to the right because I called that east. I called that my positive direction. Are there any questions about this example calculation? So this is what every single bounce apart collision is going to look like. You're going to have numbers in every single one of those, okay, as opposed to the recoil where the whole left-hand side was equal to 0. Okay, you can also organize your information in a table to help you just double check it at the end. You can see how much momentum each had before. You can see how much they had after. You can see the totals are the same. And you can look at the changes for each. The change in momentum of my 35 kilogram cart is equal to negative 43.75, the change in momentum of the 10 kilogram cart, look at that, equal and opposite change in momentum. It's the same thing we talked about with the cannon and the cannonball. So you could even fill out something like this if it helps you to see all the pieces. Now you don't have to, you're doing all that anyway in the equation whenever you solve it. But it may help you to see it, or if I ask you for that, what's the change in momentum of this object? You could go back and find just that one. All right. Is kinetic energy conserved? I told you in the notes the other day that we could have conservation of kinetic energy if it's a bounce apart collision. We could. Okay, that was the only one where we could. So let's see if it is in this particular example. Okay, so again, kinetic energy is 1/2 mass times velocity squared. So I'm going to plug in those numbers. 1/2 35 times 2 squared is 70 for the red cart. For the blue one, 1/2 10 times 3 squared is 45. So my total initial kinetic energy is 115 joules. Okay, I don't want you to forget those kinetic energy calculations. We still have to remember how to do those. Okay, at the end, 1/2 times 35 times 0.75 squared is 9.84 joules. With the blue one, 9.45. Is this going to be conserved? No, look at those numbers. They're not very similar at all. Okay, my total final kinetic energy is 19.3 joules. It is possible to have conservation of energy, kinetic energy, with a collision like this, but this particular one is not conserving that kinetic energy. This cart's probably made a lot of noise when they collided. Okay, so we don't have conservation of energy here. But I do want you to keep that in the back of your mind too, because we do still have to have those energy calculations in our back of our mind as well, because that's all part of this same unit. Are there any questions about this before we move on? I'm going to have you guys maybe try the next one on your own and see how it goes. Although the next one's kind of harder, so we'll see. All right. This one says, Tom, who has a mass of 70 kilograms, drops from rest from a 3-meter high half pipe. At the bottom of the ramp, he collides with a motionless Jerry, whose mass is 56 kilograms. The two became tangled up and slide together across the ground. How fast do they travel? Neglect friction. Okay, this one's a little trickier because I gave you more information than I did in the last problems. Okay, but we're going to start in the same way. Draw a picture. Okay, draw a picture. You can see my picture up here. Okay, but we're going to draw one as well. Okay, so here is my 70 kilogram Tom at the top of this ramp. He's gonna move down to the bottom of it. I don't even know how fast he's moving yet. I got to figure that out in a second. And then he's going to collide into Jerry. Okay, so does anybody have any idea how I might figure out how fast he's moving right here? Some of y'all are mumbling. How can we figure that out? Yeah, we have to use conservation of energy. GPE at the top will equal KE at the bottom. Yeah, we're going to combine the two in some of these questions. Okay, so because we know how high he was and that he started from rest, we can figure out how fast he's moving at the bottom, and then we can deal with the collision. So this is going to have 2 steps, okay, at least, because then they're going to stick together and move together. So that's my total picture. I got a lot of stuff going on here. So again, that may help you to draw it out, but I need to figure out how fast he's moving here so I can figure out how fast he's going when they collide so I can figure out how fast they move together afterward. A lot of different pieces. That's why I said this one might be a trickier one to try on your own, but we can see how we do. All right, so for the first step, just like Mason suggested, we're going to use conservation of energy. That's what COE is referring to. COM will be conservation of momentum. That's how I'm going to abbreviate them. We're going to use conservation of energy to find velocity. And then in step 2, we're going to use the velocity from step 1 as my initial velocity for the 70 kilogram box, which is Tom. Okay, and then solve with COM, conservation of momentum. Okay, so again, 2 parts to this problem. Okay, by the way, in case I go too fast for you, this is slide 106, because I'm going to leave it, and if you don't have the whole picture down, you might want to pull it up if you're trying to copy it. Okay, so 106 is the question. It says, All right, so energy transfer equation, which Mason already gave us. He said GPE at the top equals KE at the bottom. Okay, so MGH equals 1/2 mv squared. Take a moment. You guys should be able to do this. We've done energy. Figure out how fast he's going at the bottom. Okay, I'm going to give you all a second to try it on your own. Figure out how fast he's going at the bottom, because this part you should definitely be able to do on your own. And then we will go and look at what happens after that collision.
Great.
Still working on it? All right. Use the Inspire, your favorite calculator. I know you don't like it. But y'all, if you don't have your own, you can use something other than your phone, because you can't use them on the test. Please.
I know how to use the Inspire.
You know how to use it.
That's good.
Those Inspires are way more expensive than the other one, you know.
Yeah, 'cause there's more complicated. No, they're not.
Use a calculator. It's supposed to be easier.
It's got a touchpad and
I don't know.
You,
They don't know how to use them.
Inspire was.
Alright, looks like most of you guys got the same answer, 7.67 in that ballpark. Alright, so again, let's go ahead and look at it. Velocity, again, you should have had this, GPE 70 times 9.8 times 3 equals 1/2 times 70 times v squared. You end up with this, 2058 divided by 35 equals v squared, which is equal to 7.67 meters per second. All right, so we know how fast he's moving now when he collides. So now that we know that, we can actually deal with the collision part. Okay, so part 2 is now we're dealing with a collision, so now we're dealing with conservation of momentum. We did our conservation of energy. Looked like y'all were pretty good with that. Okay, so we now have these two objects. Let's label our givens. M1 is 70. V1 is 7.67. That's rounded, so you can use the whole value if you want to, or we can just use the rounded one for this. Since it's not my open math, it doesn't really matter that much. Our object 2, 56 kilograms, is initially at rest. Okay, that's before. After the collision, I still have that same 70 kilogram object. I don't know how fast it's moving. I still have that 56 kilogram object. I don't know how fast it's moving, but I do know this. They're stuck together. So I know it's moving the same speed as the first guy. Okay, Tom and Jerry are now moving the same speed. So I know that V2F is equal to V1F because it says they're stuck together. They get tangled up. Okay, so in terms of our collision types, this is obviously a stick-together collision. And this is what all of your stick-together collisions are going to look like. Their final velocities will be the same because they're stuck together. Okay, so our equation is the same as it was before, but now you'll notice instead of V1F and V2F, I just wrote VF because it's only one variable now. They're equal to each other. So it's the same final velocity for both of them, which makes it a like term in my calculation. It's going to make my math easier in a second. So let's go ahead and substitute in, and we get this. 70 times 7.67 plus 56 times 0 equals 70 times VF plus 56 times VF. And again, that's the same VF for both because they're stuck together. You can only do that if they're stuck together. Okay, if they're not stuck together, it's V1F and V2F. All right, that becomes this. 536.77 plus 0 equals 70 plus 56 times VF. Okay, I just combined those like terms together. So again, here is my total initial momentum. I already know what it is, which means I already know what my total final momentum needs to be equal to. And that's what this statement is doing. It's setting it equal to that. So I have that equals 126 times VF. If we divide both sides by 126, we get a final velocity of 4.26 meters per second. Okay, and so that is the final velocity for both of them because they are stuck together. So that is the answer to that question that we just were asked is how fast are they moving after they collide. 4.26 meters per second. Notice it's slower than his velocity was initially because we gained mass when they collided and stuck together. We talked about that in our notes a couple days ago. Questions about this calculation? By the way, all of your stick-together collisions are going to look like that. You're only going to have one final velocity to deal with because they're stuck together. All right, follow-up question. Let's bring it back to energy again. Why not? How far will the two travel up the other side of the half-pipe ramp? Now that we know that we have both of them moving at 4.26 meters per second, how high will they go whenever they slide up that hill? Because they've got an initial velocity now. So we're going to write our energy transfer equation. We know we have this kinetic energy of this system, the two stuck together, and we have a speed. So we know we have kinetic energy. And as they go uphill, what's it turning into? Gravitational potential energy. There's our equation. The KE that they have at the bottom will be equal to the GPE they have at the top, if there's no friction, which we're assuming right now. So 1/2 mv squared equals mgh. Okay, and we can solve for height. Guys, what's my mass going to be? It's going to be the sum of the two together, right? Because they're moving together. So it's not just Tom, it's not just Jerry, it's 70 plus 56. We're going to add them together to get the total mass of that system. So 1/2 times that total mass times v squared equals GPE. There's my total mass, 70 plus 56 times 9.8 times height. We get this. It's 126, by the way. That's their total mass. 1/2 of 126 times 18.15 equals 126 times 9.8 times height. If we continue solving and divide, we get this. The height will be equal to 0.926 meters. Again, coming back to energy again. We can't forget this. It's on our test too. Questions about this one? No? Okay, so this is a tricky problem, but there are some like this on the assignment that do require you to remember your conservation of energy and your conservation of momentum in the same question. You're working on the assignment today, 905.2 conservation of momentum calculation problem set. It is due by 11:59 p.m. tonight. You have about 16 minutes left in class, so you've got enough time to try a few of these while you're in here and make sure that you ask questions if you get stuck. Don't forget also your RA is due next Wednesday on the 21st. You can finish that outside of class or anytime you have extra time in class. You also have a quiz and a test next week. Next Wednesday's your quiz, next Friday's your test. So don't forget about your unit summary as well. If you're struggling and want extra practice, or just if you want extra practice, that's in there too. All right, guys, go ahead and get to work. If you have any questions, please let me know.